right, and we're back on stage. So this time I'm not going to speak about AI engineer in Paris. I'm going to speak about what we actually do and how we see AI continuously redefining cloud infrastructure. My main job is to run a company called Koyeb. And as Rauf mentioned, I've spent the last 14 years in the space of infrastructure in general. So I've seen a bunch of evolution from the beginning of cloud infrastructure to now and this new wave with AI. So we're going to spend 20 minutes together looking a bit about the evolution and what is coming next with the agentic era. So the first thing I want to highlight is if you look a bit back, so 2 years ago, 3 years ago with Gen AI engineering, the main thing which popularized AI engineering is LLMs backed by GPUs. So typically ChatGPT and all this, the OpenAI models were LLMs running on GPU. So if you look at the early 2023 AI stack, 2.5 years ago, it was relatively simple in the sense that in terms of number of components, you used to have like an API, vector databases on one end, then you had a limited choice of models. So typically in early 2023, you had the GPT models from OpenAI, closed source, and you had a few open source models, so the Llama models from Meta and Stability AI. But Mistral wasn't even there, for instance, and it was running on GPUs with a Triton inference server, probably simply because even VLLM didn't exist, and we're speaking of only 2.5 years ago. But now AI engineering is also content engineering, VLMs, so models which include like image and vision capabilities, video models, vibe coding, a big trend of this year, MCP and agents. We see all of this as an infrastructure provider, and I want to dive a bit with you on what the future of AI infrastructure looks like, and how we are trying to build for this agentic era and what are the changes we see. So the agentic AI stack is way more sophisticated. I picked a set of technologies which we see in this new stack. So it goes from the front end, which is regularly vibe coded. So we have app.build, Manus or Lovable to vibe code your front ends. Our team made an experiment on this, which you can see on the expo floor. We have APIs which might be in more diverse languages because you have more SDKs available. You have the agents, which are probably going to be written in Python still, but are different like components. And then even the historical databases have vector capabilities or capabilities for AI. Then you have MCP, and for the execution and the inference of the model, you have also more diversity. So IAMD is a credible player now and can be used for specific models. So you might have an image model running, a video model running on a different kind of hardware, or LLMs running on an accelerator here, for instance, Tenstorrent, which is an upcoming provider of hardware trying to disrupt the NVIDIA market, the market of NVIDIA. And you might not even see any of this because you might also be operating on a higher level of the stack with the inference endpoints. So if you look at what it means in terms of hardware infrastructure and infrastructure to operate, now it's a mix of GPUs, CPUs, and accelerators. You have large training, which is still performed with GPUs, fine-tuning and small training where you will probably still have GPUs, inference where you can have accelerators, and people are probably today starting to train with AMD GPUs. But inference is where you're going to see mostly AMD GPUs, and then agentic workloads, which are actually running on the good old CPUs. Now let's dive into agents. I want to actually start by defining what is an AI agent, how we see it. And because the definition of agent varies highly, so the simple definition, if you look it up, is it's going to be a software system that uses AI to pursue goals and complete tasks on behalf of users. They show reasoning, planning, and memory, and have a level of autonomy to make decisions, learn, and adapt. For us, there is a key question of what is important in this definition, what impacts infrastructure. So it's software system. At the end, it's still like Python or TypeScript or another language which is going to run on our servers. It's going to complete tasks, and they have a level of autonomy. And what it means, technically, is that the level of autonomy, you're going to run untrusted code in general, which is generated by a model which is non-deterministic. So anybody who ever worked in security should think about like the danger that it involves, and actually the requirements it involves. And the first requirement we see with agentic workloads is secure sandboxed environments. So to make sure that this untrusted code is not dangerous to your production platform or environment. We see requirements in terms of performance because they still need to run fast. The agents are mostly ephemeral, so they run for a short period of time. Because there is a high volume, efficiency is a key topic, and the deployment speed is also a key topic that we see. Now, on the Koyeb side, we build a global serverless platform, and we use this for agents and inference. So we provide a diverse set of hardware to support all these use cases. And I'm going to briefly show you. I'm going to do a live demo if it goes well. And we're going to execute sandboxed codes using the Koyeb MCP server. Let's do it. All right. So. We are going to use Claude with MCP connector here. So it's called Koyeb Sandbox. What it's going to do, technically, it's going to create a sandbox to execute our untrusted code. Today will be relatively safe. We'll execute some simple addition. But we'll see how what happens behind the scene. So here I have something which is pre-configured. If I have, okay, it should be fine. Which is pre-configured which should be pre-configured to run using the Koyeb Sandbox project. That's interesting. Okay. So we do have network here, and basically, okay, here we go. So I'm going to, it basically instructs the agent to use a Koyeb sandbox to execute untrusted code. So what we're going to do now is we're basically going to ask him to execute untrusted code. Can you please execute this untrusted code? And it's going to use our MCP server to create a sandbox. All right, so here we have the account technically where we run the MCP server already, and we're going to see sandbox being created behind the scene. So typically, we've done this demo with Claude. It could be done with anything else. So we also have a demo running with like Mistral to create the sandbox. Here we see that it's creating a sandbox called calculation sandbox, and that it's getting created behind the scene by the prompt. And so eventually, this sandbox is healthy, and we are going to get the result here. Now, let's look at what's happening behind the scene and what it means. Right now, I just did this quickly. I went to Claude. I executed code. but coding agents are doing this automatically for you without you specifically asking to do it. So behind the scene, as a service provider, what we see is that agentic workload need to create thousands of secure sandboxes daily with sub-second starts. Like in this case, you want the result to be immediate. And this year is a year where we started seeing people coming to us telling us, hey, we need to deploy 10,000 containers a day because we have this agentic workloads which do this automatically. So if you use Lovable, behind the scene, they are going to automatically do this for you, and they are going to create a container on an infrastructure provider like us. AppTopBuild, for instance, is doing this on Koyeb. One of the key questions for us from a technical standpoint is how fast can we boot an agent, and how many agents can we boot so that the experience for end users is seamless. The technical problem behind it is we deploy Docker containers, so they are stored in our registry, and we need to transform them in an agent executing your code. Behind the scene, our stack is actually leveraging virtualization to isolate the containers. So we use Cloud Hypervisor to run the container. We have, and on top of this, we have the container, the agents, and we might have, if it's an inference workload, we might have an inference engine like the LLM. And below, we're operating on bare metal machine. So when someone types a prompt like this, we need to get this all ready. The bottlenecks are multiples. So you have multiple bottlenecks, knowing that we're aiming to get sub-second like start. So if you were to create a bare metal server from scratch, it would take minutes. If you want to pull an image from a registry, it can take several seconds for small images. If it's a large model, it's going to be way longer. Your networking is going to be a problem because you have to converge between all your servers, so networking configuration. And then you also still have to execute the runtime of your agent. So typically, the Python runtime is going to take some time to start. In our case, one of the main bottleneck when we started seeing this increase of volumes was networking. Some people might think it's actually the virtualization engine. Firecracker has been quite popular lately, even so it's not totally new. But in practice, for us, the virtualization engine is not the bottleneck. In most cases, it's really the networking part, and it might even be something completely different in your system. So if you have a vault system, it might starting to take a lot of requests and just like be the bottleneck. We were able to mitigate most of this problem, so we preemptively start the machines, we cache the images on the hypervisors, and on the networking side, we made a lot of optimization to reduce the time. And the last part which we don't control is actually the agentic runtime, which we don't optimize the Python runtime ourselves. So this part is still like one of the components which might take time to start. We do have a mitigation though, to be able to for this workload, to support this workload. And the mitigation is actually called scale to zero. That's how we mitigate most of the cold start. So let me back up a bit. If you're on the agentic workload, we have two key patterns. You have ephemeral sandboxes, which are going to be executed like during 1 minute. And if you are, for instance, using Lovable, it's going to create a web server at the end, which is going to run constantly. One of the challenge for these providers is a lot of people try it out, and then you have a huge fleet of services which are actually idling most of the time. And so, but someone might still be using them, and they are looking to maintain it up and running. So to mitigate this problem of cost, we scale down to zero the workloads. If you've been in infrastructure in the past, one of the challenges when you scale to zero is how fast you can restart the server, because we completely shut down the VM, and so you will hit this time of startup. So we have two techniques like scale to zero and auto-scaling to increase efficiency, and we're able to reduce cold starts with snapshots. So what we do technically behind the scene is we do memory snapshots. So your agents, we're going to save the memory. We call this mechanism light sleep, and basically it reduces the cold start time from several seconds to 100, 200 milliseconds, which is not visible at all for end users. And so we end up being able to manage large fleets of machines without increasing your cost as an operator of such a technology. This is available now on CPU. This technology, we also have scale to zero on GPU. We're bringing the same principle of memory snapshotting to GPU too for this kind of workloads. If you want to know more, you're welcome to get started with our platform, and we have our engineering today on site. So please don't hesitate to ask them any question if you're curious about how it can be helpful. Thank you, everyone.